What really happened at the time of the Big Bang? Dear traveler, a warm welcome. Today we are embarking not to the edges of the universe, but to its very origin. A mysterious moment, a heartbeat in time, where everything we know, space, matter, energy, and even time, would have burst forth from an infinitely small point. This is the theory of the Big Bang, a universe born 13.8 billion years ago, expanding ever since. But this vision is not the only one. Some speak of a cyclic universe that is born, dies, and is reborn in an infinite series of Big Bangs and Big Crunches. Others imagine a big bounce, a cosmic rebound, where an ancient universe collapsed before giving birth to ours. So, what was there before the Big Bang? Break time. Gee whiz. But before setting out on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a good journey. The Lambda CDM model, or Standard Cosmological Model, describes the evolution of the universe from an extremely dense and hot initial state, known as the Big Bang. Dominated by the presence of a cosmological constant, called lambda, and a form of cold, non-relativistic matter, it is today the major reference for explaining the dynamics and large-scale structure of the cosmos. Despite its remarkable successes, some recent observations and fundamental questions suggest that it might be necessary to go beyond this framework. To understand what drives researchers to explore other avenues, we must revisit the definition of the Big Bang, the conceptual problems it raises, and the tensions that have appeared in recent years. In the collective imagination, the Big Bang evokes a gigantic explosion at the origin of all current matter and energy. In reality, in scientific terms, it refers to an extremely dense, hot, and rapidly expanding initial state from which the universe emerged about 13.8 billion years ago. The density represented the amount of matter per unit volume, and the temperature measured the thermal agitation. In these conditions, the fundamental particles were in constant collision, maintaining a balance between opposing nuclear reactions. With expansion, the temperature dropped, allowing the formation of light atomic nuclei, then entire atoms. This vision prevailed thanks to discoveries like the fossil radiation, a luminous remnant from the time when the universe was still uniformly hot. The Big Bang theory, supported by general relativity and solid observational data, explains many phenomena, but it hits some snags. The most notable is the initial singularity, a theoretical state where density and temperature would be infinite, incompatible with known physical laws. This reveals our limitations in understanding the extreme conditions of the beginnings. In relativity, mass and energy curve space-time. However, going back far enough, this curvature becomes such that no coherent description is possible. A more complete theory, integrating quantum gravity, could reinterpret or eliminate this singularity, thus avoiding this conceptual blockade. Another issue is the horizon problem. It describes the maximum distance light could have traveled since the onset of expansion. Yet, very distant regions exhibit surprisingly homogeneous properties, as if they could have exchanged heat, which is impossible within the classical model framework. This is the horizon problem. To address this, the idea of cosmic inflation was proposed, a phase of explosive expansion early in the universe's history. But even this scenario doesn't solve all the mysteries, and some physicists are exploring more daring theories to provide a more natural solution. The apparent flatness of the universe also raises questions. The global curvature of space depends on the total density of energy and matter relative to a critical value. If, initially, this density had been slightly different, the universe would have quickly evolved towards a strong curvature, leading either to a collapse on itself or to uncontrolled expansion. Observations, however, show that it is almost perfectly flat. Inflation can smooth out this geometry, but why it would have exactly the required characteristics to achieve such a result without arbitrary adjustments remains an open question. The lambda CDM model also assumes the existence of forms of energy and matter whose deep nature remains unknown. Dark energy would explain the current acceleration of expansion, while dark matter would account for the cohesion of galaxies and the formation of large structures. Yet, despite decades of research, no direct or indirect evidence has identified these components. Attempts at detection have so far yielded no conclusive results. Observational tensions have complicated the picture. The most well-known concerns the Hubble constant, which measures the current expansion rate. Data from the cosmic microwave background provides one value, while local observations indicate another, significantly higher one. This discrepancy, known as the H0 tension, exceeds simple measurement errors and could signify a methodological bias or the need to adapt the model. Another divergence concerns the S8 parameter, which measures the magnitude of large-scale density fluctuations, and again the model's predictions do not perfectly match the observations. These discrepancies do not undermine the contributions of the model, but encourage its evolution. Some propose adding interactions between dark matter and other components, or imagining dark energy with intensity varying over time. Others modify gravity itself on a large scale to simultaneously solve several problems. These approaches remain speculative and require solid validation. The fundamental limit comes from the gap between general relativity and quantum mechanics. The former describes gravity on a large scale, but not the microscopic world. The latter explains the behavior of particles, but does not naturally apply to the cosmic scale. Theories like loop quantum gravity or string theory aim to bridge this gap, but no fully validated unification exists yet. Added to this is the question of energy hierarchy. The conditions of the Big Bang involved energies far superior to those our accelerators can produce. Early physics is thus based on uncertain extrapolations. Reproducing these conditions in the laboratory would allow more direct testing of our theories, but remains out of reach for now. Faced with these challenges, the scientific community wants to build a unified theoretical framework connecting particle physics and the expansion of the universe. It should explain the nature of dark energy, the exact role of dark matter, and the initial mechanisms that shape the cosmos, whether it be inflation, rebound, or other innovative scenarios. New telescopes, detection experiments, and space missions provide tools to probe these mysteries with unprecedented precision. The subtle discrepancies between the lambda CDM model's predictions and observations could be the key to a broader cosmology, encompassing all high-energy physics and the secrets of the young universe, while extending our understanding beyond the Big Bang. In the middle of the 20th century, three scientists, Hermann Bondi, Thomas Gold, and Fred Hoyle, presented a bold vision of the cosmos, different from the dominant idea that the universe was born from a dense and hot state. This concept, known as the stationary or steady-state model, is based on a central principle, the perfect cosmological principle. Imagine a narrator guiding us in an infinite space, amid shimmering galaxies, witnesses to an eternal dance, without beginning or end. It is in this setting that we discover how these researchers wanted to reinvent cosmology and why their proposal initially captivated. This principle asserts that the universe is homogeneous and isotropic, not only in space, but also in time. Homogeneous means that from one point to another, the universe presents the same appearance and average density. Isotropic indicates that it remains the same in all directions. This idea extends the ordinary cosmological principle, which assumes spatial uniformity, but adds temporal constancy. The real novelty lies in the idea that the universe does not change through the ages. Its density, structure, and general appearance of galaxies would remain identical. Bondi, Gold, and Hoyle accept the expansion discovered by Edwin Hubble in the 1920s, but introduce an unprecedented mechanism, the continuous creation of matter. Thus, despite the enlargement of space, the density remains stable because new particles constantly appear. To formalize this concept, they introduce a creation parameter, noted C, representing the spontaneous birth of particles per unit of volume and time. The image is simple, a rising dough, in which fresh dough would continually form, maintaining the same concentration around the raisins that are the galaxies. This idea, however, raises questions. How could matter spontaneously appear? It implies a new physics, allowing to bypass the strict conservation of energy and matter. But for its authors, this price to pay preserves the elegance of an eternal universe. At the time, this perspective appeals to those wishing to avoid the notion of an initial singularity, where density and temperature would be infinite. The steady-state model also predicts that the luminosity function of galaxies remains unchanged. To compensate for the creation of new galaxies, an equivalent number would disappear or evolve, ensuring a constant overall population. In this vision, there is no last scattering surface, no primordial hot phase followed by cooling, thus no wall of photons dating back to a dense and hot era. The universe, eternally similar to itself, has no temporal boundary where light would have begun to travel freely. In the 1940s and 1950s, this hypothesis seduces, as observations are still limited. Telescopes lack power, and radio astronomy is in its infancy. The steady-state model seriously rivals the idea of a universe having a beginning. But in the mid-1960s, the discovery of a diffuse and uniform microwave radiation, the cosmic microwave background, changes the game. This signal, a remnant of a young and hot universe, directly contradicts the steady-state theory. In an eternal and stable universe, nothing explains such homogeneous radiation about 3 degrees above absolute zero. Proponents attempt to see it as the result of radiation emitted by stars or galaxies, but the observed spectrum matches that of a black body, impossible to reproduce by a mix of varied sources. Radio source counts, like quasars, worsen the situation. The further we observe into space, therefore into the past, the more these objects are abundant. This indicates that the universe evolves over time, which the steady-state model refuses. Adjustments attempted by Hoyle and his colleagues make the theory more complex without solving the problems. The subsequent discovery of tiny fluctuations in the cosmic background, thanks to satellites like COBE, WMAP, and Planck, further strengthens the idea of an initial hot and dense phase. Today, the scientific community considers the steady-state model refuted, but it played a major role in driving research to design discriminating tests and refine observations. It fed the philosophical reflection on cosmic eternity and inspired other alternative models. This episode illustrates the strength of the scientific method. When a clear prediction is contradicted by facts, the theory must yield. The steady-state model did not survive the fossil radiation nor the radio source surveys. It, however, marked history, reminding us that scientific progress arises from bold hypotheses, controversies, and humility in the face of data. Thus ends the story of the steady-state model. Conceived as an elegant alternative to a universe with a beginning, it collided with decisive observations. Its disappearance does not erase the legacy it leaves, the demonstration that by confronting our ideas with the sky, we gradually draw the true portrait of the universe. In this chapter, dedicated to the theory of cosmic plasma, we explore an alternative vision of the history and structure of the universe. Imagine a documentary commentary, like a space journey through unsuspected regions, guided by those who explain the cosmos through electricity and magnetism. In this approach, gravity would not be the only force at work. Immense electric currents and magnetic fields would shape the universe over incredible distances. To better understand, let's revisit the emergence of this concept, its foundations, and its challenge to the notion of the initial singularity. We will also see its explanations on galactic filaments and the cosmic web, as well as the difficulties it faces with certain observations, such as the overabundance of light isotopes or the interpretation of diffuse radiation on a large scale. Plasma designates a fourth state of matter, different from solid, liquid, and gas. It results from the dissociation of atoms into charged particles under the effect of high temperatures or intense electromagnetic interactions. On Earth, it can be found in lightning or fluorescent tubes. In space, it is ubiquitous. The Sun and most stars are almost entirely composed of it. The precursors of this theory estimated that electricity and magnetism could influence the formation and organization of galaxies. At the beginning of the 20th century, Norwegian Christian Birkeland proposed that cosmic currents circulating in polar regions explained the auroras. He highlighted structures we now call Birkeland currents, columns of plasma carrying enormous electrical charges. Gradually, other researchers extended his work to galactic scales, suggesting that such phenomena could structure the entire universe, shaped by intergalactic magnetic fields and colossal currents. With the development of plasma physics in the 20th century, scientists like Hannes Alf Venn suggested that on astronomical scales, plasma could form filaments under the combined action of gravity and electromagnetic forces. In this vision, there is no need for an initial singularity. The universe would be an immense plasma whose energy reorganizes into gigantic conductive circuits. These filaments would constitute the true framework of the cosmic web, connecting galaxies and clusters. These filaments would concentrate matter at the points where they intersect, promoting the birth of galaxies. Gravity would play a role, but it would be complemented by powerful electromagnetic forces. Plasma would allow energy transfer through double layers, zones of high electrical tension capable of accelerating particles to speeds close to the speed of light. Observed in laboratories as well as in space, they could, on a cosmic scale, locally heat matter, trigger star formation, or eject particles into the void. According to this scenario, the cosmic web would not result solely from gravity and expansion, but from electromagnetic gradients and tensions drawing filamentous networks. This approach proposes an alternative to the classical explanation of large structures, where gravity alone would struggle to account for their scale. Proponents of this theory argue that a primordial, vast, and ionized universe always existed. Rather than a Big Bang, matter would have been organized gradually by electrical and magnetic interactions. Some even envision an eternal universe. While not all reject the idea of expansion, many refuse the notion of a unique initial singularity, preferring to seek other interpretations to explain cosmic evolution. This view relies on various clues: filamentous shapes of nebulae, massive magnetic fields between galaxies, ultra-fast particle jets. Laboratory experiments show that plasmas spontaneously generate spirals and filaments, analogous to some structures observed in space. Traditional cosmologists, however, consider that gravity suffices within the standard framework to explain these forms. Intergalactic filaments, in this perspective, could extend over millions of light years, connecting galaxy clusters like a vast cosmic bloodstream. The observed matter web would be the direct expression of electromagnetic force lines. Galaxies would form and arrange themselves thanks to self-organizing processes inherent in plasmas. However, this theory faces several obstacles. It struggles to explain the proportion of light isotopes observed in the universe, consistent with Big Bang model predictions, but difficult to reconcile with a universe without an initial singularity. Proponents suggest alternative nucleosynthesis scenarios, but none perfectly reproduce the observations. Another challenge: large-scale diffuse radiation, interpreted by standard cosmology as the thermal echo of a dense and hot primordial universe. For cosmic plasma, explaining its isotropy is more complex. Some invoke giant electromagnetic interactions, but their calculations rarely match the precise measurements available. Despite everything, the theory persists, encouraged by new observations, polarization maps, radio surveys, sensitive imaging techniques. Its proponents hope to clearly detect highly ionized filaments linked to local phenomena of star formation or matter disturbances. It offers a striking vision of a universe traversed by cosmic flashes, where galaxies are like pearls strung on energy wires. But the question remains, can this model truly account for the observed chemical composition, the uniformity of the diffuse radiation, and the overall dynamics of the cosmos? Traditional researchers believe that this approach underestimates the evidence of primordial nucleosynthesis and the thermal history of the universe. Plasma theorists, on the other hand, think that classical cosmology places too much emphasis on gravity and dark matter, and not enough on electromagnetism. All are waiting for future observations to decide. Our exploration of the concept of classical cyclic universe begins with the work of physicist Richard Chase Tolman, who proposed that the universe could experience a series of expansions and contractions, rather than a single phase of expansion from an absolute beginning. In this view, it expands, cools, forms structures, then eventually contracts. After a maximum contraction, a bounce can occur and mark the beginning of a new expansion. Imagine a balloon that inflates and deflates periodically. Each cycle alternates between expansion and contraction without requiring an impossible to retrace initial moment, contrary to the traditional Big Bang hypothesis. A key element of this vision is the progressive accumulation of entropy, a measure of the order or disorder of a system. For Tolman, each cycle adds an additional amount of entropy. During the expansion, matter cools, and irreversible processes, such as star formation and evolution, increase this disorder. During the contraction, the entropy does not decrease, because according to the laws of thermodynamics, it grows or remains constant. Cycle after cycle, this total entropy accumulates, influencing the evolution and duration of the following phases. For a cyclic universe to be possible, it must have a positive global curvature or closed geometry. This means that on a large scale, the sum of the angles of a huge triangle exceeds 180 degrees, a sign that space curves back on itself. In this framework, the contraction can continue to a point of rebound, provided that the cosmic viscosity, that is, the internal friction of the universe's contents, remains sufficiently low to avoid a definitive implosion. If this viscosity is minimal, a bounce can initiate a new cycle of expansion. Thermodynamic effects play a major role in this scenario. With each cycle, entropy increases, making the universe more disordered on a large scale. This accumulation alters the amplitude of the oscillations. When expansion restarts, it does so in a state already altered by the previous cycle, which can generate more energetic oscillations, as long as the conditions for a rebound remain met. This model is not, however, without controversy. A rebound might require forms of matter with negative energy, difficult to reconcile with current theories. Moreover, general relativity, despite its successes, does not always suffice to explain the transition from a full contraction to a new expansion. Some researchers therefore consider modifying it or resorting to theories related to quantum gravity. Without observational evidence of such components or corrections, the idea remains speculative, though appealing. To better understand the notion of positive curvature, one can imagine a closed space like a sphere. Traveling in a straight line long enough, one would return to the starting point. In a flat universe, such a trajectory would continue infinitely. In an oscillating scenario, this closure plays a crucial role. When the expansion exhausts, gravity takes over and causes contraction. If the viscosity remains low, density and temperature increase up to a rebound that relaunches expansion. This back and forth illustrates the heart of the cyclic model. Cosmic viscosity, though rarely mentioned, is a determining parameter. It measures the internal resistance of the universe's components to movement, much like oil in an engine. If it's too high, contraction could become irreversible, leading to a big crunch. If it's weak, some repulsive forces could counteract the compression and allow for a bounce. The balance is delicate. Too much dissipation prevents restarting, too little doesn't sufficiently slow the contraction. Finding this equilibrium point is a major challenge. The perpetual increase of entropy is one of the most intriguing aspects. According to the second law of thermodynamics, it can only grow or remain stable. Each cycle accumulates more, altering the initial conditions of the next one. If this continues indefinitely, entropy could reach such a high level that the universe would approach heat death, where energy is so dispersed that no structure can form. The question then arises, can cycles really repeat infinitely? The contraction phase raises other challenges. As the universe shrinks, density and temperature increase, activating various physical processes. If the contraction reaches extremely small scales, general relativity effects become dominant, sometimes requiring corrections from advanced theories. Some physicists believe that quantum gravity could prevent the formation of a final singularity, introducing a repulsive effect at very high densities, thus paving the way for a bounce. Observational data are essential to test this model. Cosmologists measure, among other things, the Hubble constant, and the distribution of galaxies. A cyclic universe should leave certain signatures, such as traces of events prior to the current expansion. But no clear evidence has been found, and the current composition of the universe corresponds well with the standard model of a single expansion, hence the caution of the majority of researchers. The actual amplitude of the oscillations is another open question. If the density at the bounce is too high, the conditions would approach those of a singularity, making the cycle unstable. If it's moderate, some form of energy or pressure must balance the contraction. Some models propose integrating a phase of cosmic inflation after each bounce to homogenize and reinvigorate the expansion. The concept of a classical cyclic universe was born at a time when observations were limited. Tolman formulated his ideas before the discovery of the cosmic microwave background, this fossil radiation that testifies to a very hot past. Today, our measurements of the universe's composition and background radiation rather confirm an initial Big Bang, followed by a continuous expansion. But a cyclic scenario remains conceivable if each bounce can preserve or reorganize this radiation. The proponents of this model point out that the Big Bang doesn't solve everything. Initial singularity, horizon, and flatness remain open questions. An oscillating universe could avoid the singularity, homogenize the temperature, and regulate the geometry. But these hypotheses require precise calculations and sometimes clash with observations of the formation of elements or galaxy structures. To test or refute this scenario, researchers rely on numerical simulations and fine analyses of the cosmic microwave background, gravitational waves, and large structures. These efforts aim to determine the exact conditions for a stable bounce. The future of the concept hinges on this confrontation between theory and observation. Imagine a vast cosmic landscape, an immaterial setting where time curves and matter seems to arise from fundamental laws difficult to conceive. In this hypothetical journey, we discover the quantum Big Bounce, a scenario that attempts to solve the ancient problem of the initial singularity, that point where density and temperature would reach infinity within the framework of the classic Big Bang. Scientists have always sought to understand how the universe could have originated without violating the laws of physics, especially those governing gravity at infinitesimal scales, close to the Planck length. The quantum Big Bounce emerges from the desire to unite general relativity, which describes the universe on a large scale, and quantum physics, which explores the microscopic. Here, quantum effects would prevent the universe from contracting to a dimensionless point. To understand this theory, let's focus on loop quantum gravity. Unlike general relativity, where gravity results from the curvature of a continuous spacetime, it imagines a spacetime made up of discontinuous elements, similar to tiny loops or rings of information. Space would not be smooth, but pixelated by imperceptible geometry quanta. These networks of connections would define the quantum state of geometry. According to this approach, when the density reaches a critical threshold, specific effects appear to counter the total collapse of matter and energy. Gravity, instead of intensifying, would reverse its effect, causing a bounce. This threshold is called the critical density, often denoted R-ho critical. For the universe described by loop quantum gravity, it would represent about 0.41 times the Planck density, the highest theoretical volumetric mass possible. Beyond this threshold, spacetime stops collapsing and initiates a bounce, giving rise to a new phase of expansion. Thus, instead of a definitive crush, the universe changes phase, somewhat like a spring that, having reached its compression limit, forcefully expands. Technically, this idea is expressed by a modified Friedmann equation. In standard cosmology, this equation links the rate of expansion of the universe to its total density of matter and energy. In the quantum big bounce, a factor of 1 minus the density divided by the critical density is added. As long as the density remains below this threshold, the expansion follows a classical course. Once crossed, the factor becomes negative and triggers the bounce, replacing the singularity with a contraction-expansion cycle. The absence of an initial singularity opens up fascinating possibilities. The universe could originate from a previous contraction phase, where matter and energy would have reached an extremely dense, but not infinite, state before bouncing towards the current expansion. Temperatures at the moment of the bounce would be immense, but finite. This model preserves the validity of physical laws at the most extreme densities, where classical approaches lost all predictive power. If the universe has bounced, some traces might persist today. Scientists study the scalar spectrum of the cosmic microwave background, the luminous vestige of the first moments, to detect clues dating back to the contraction phase. They are looking for distinctive signatures that would differentiate this scenario from that of standard cosmic inflation. To go further, researchers are interested in primordial B modes, a specific form of polarization of the cosmic microwave background, potentially generated by gravitational waves at the time of the bounce. Detecting such a pattern would constitute a major observational proof, despite the difficulties related to their extreme weakness and galactic interferences. Space missions and polar telescopes are actively working on their detection. The quantum big bounce not only describes a contraction-expansion transition, it also offers a new vision of cosmic causality. It could solve the horizon problem by allowing the contraction phase to homogenize the universe before the bounce. The cosmic history would then extend over much longer periods than imagined, integrating this contraction into its narrative. Numerous theoretical works explore the precise mechanisms that would prevent the singularity. Although the critical density is estimated at about 0.41 times the Planck density in simple models, this value varies depending on initial conditions and the coupling between matter and geometry. The central idea remains that near Planck density, spacetime can no longer be continuous, and quantum corrections impose a natural limit to the collapse. This model also opens up perspectives on the future of the universe. The expansion might, in a distant future, slow down and then reverse, leading to a new contraction followed by another bounce. An endless cycle of cosmic breathing could thus be envisioned without absolute beginning or end. To validate this theory, cosmologists turn to ultra-precise measurements, mapping the cosmic microwave background, studying the distribution of galaxies, detecting primordial gravitational waves. Patterns or anomalies unexplained by classical inflation would reinforce the bounce hypothesis. Despite its appeal, the theory raises questions. The link between loop quantum gravity and the observed particles or forces remains to be clarified. The dynamics of the bounce could also be influenced by components such as dark energy. Stability in the face of quantum fluctuations is also in debate. Beyond the technique, the idea fascinates. If the universe has bounced, there was something before the Big Bang. This questions the very notion of the beginning of time, which the Big Bounce could replace with an eternal transition between states of the universe. Researchers are now awaiting future observations, particularly those on the polarization of the cosmic microwave background, which could differentiate the Big Bounce from classical inflation. A confirmed detection of primordial B modes would mark a historical turning point, eliminating the idea of an initial singularity. Welcome to a captivating exploration of a cosmic scenario that offers a different vision of the history of our universe, avoiding some issues encountered by the classical model of expansion from an extremely dense initial state. Here, we will delve into the ekpyrotic model or cyclic universe, imagined notably by Justin Curie, Paul Steinhardt, and Neil Turok. On this journey, we will discover concepts where the notion of brains, ultra-rigid contraction, and cosmic rebound play a central role in explaining why the universe might experience successive cycles of expansion and contraction. This model, distinct from the traditional Big Bang, describes a universe reborn through the collision of multidimensional structures. Prepare for an amazing journey into a 5-dimensional cosmos. To understand what ekpyrotic means, let's go back to its origins. The term comes from an ancient idea evoked by Greek philosophers, a purifying and cyclical cosmic fire. In some visions of ancient Greece, the universe underwent infinite phases of destruction and rebirth. Modern cosmologists drew inspiration from this image to describe a universe alternating contraction and expansion endlessly. In the model advocated by Curie, Steinhardt, and Turok, the story unfolds beyond the 4 known dimensions. It introduces at least one extra dimension, in which our observable universe would be a brain, a membrane evolving in a 5-dimensional space, the bulk. One can imagine it as a vast hall where several 4-dimensional membranes float. Our perceptions, limited to 3 dimensions of space and time, are confined to one of these branes, while the extra dimensions, invisible, influence cosmic dynamics and cyclicity. The key element of the model lies in the possible collision between 2 branes within this bulk. Imagine 2 flexible sheets moving and eventually colliding. The energy released by this impact transforms into heat, giving birth to a dense and hot universe, the beginning of a new phase of expansion. Here, the Big Bang is not seen as an initial singularity, but as the consequence of a cosmic collision between branes, producing the matter and radiation of the primitive universe. Before this collision, a contraction phase is necessary. In the ekpyrotic scenario, it is described as ultra-rigid, dominated by extremely high pressure. This peculiarity allows for the generation of the density fluctuations required for the formation of galaxies and cosmic structures. In this context, the produced perturbations are almost scale invariant, which corresponds to what we observe in the cosmic microwave background and large-scale structure. Thus, during contraction, energy simulating a very rigid fluid dominates the universe. Quantum fluctuations from the fields at play form before the bounce, ready to shape the expanding universe. The model therefore offers an alternative to cosmic inflation, capable of producing similar fluctuations, but without ultra-fast expansion. The bounce, a key moment of the scenario, translates into the collision of 2 large, 4-dimensional branes in the bulk. The energy accumulated during contraction is released, heating matter and radiation. This process, repeated cycle after cycle, could extend over an infinite duration without an absolute beginning. As with any cosmological theory, this model must be compared with observations. For instance, it predicts a very low production of primordial gravitational waves, contrary to inflation. A significant detection of these waves would therefore go against this view. It also anticipates a particular form of fluctuations characterized by negative local non-Gaussianity, which could distinguish it from other models if this signature were to be confirmed. This scenario challenges the notion of the universe's beginning. It proposes an eternal, cyclical cosmos without an initial singularity, where each collision resets certain properties. However, it presents theoretical challenges, notably on the smooth transition between contraction and expansion, and on the precise dynamics of the branes, often explored within the framework of string theory. Despite these difficulties, the appeal of a cyclic universe remains strong. It naturally explains large-scale homogeneity and links the birth of the hot universe to a concrete physical event. The future of this hypothesis will depend on observations, measurements of the cosmic microwave background polarization, large-scale matter surveys, and the possible detection of unique signatures left by past cycles. This journey into the heart of the ekpyrotic model shows that the universe might never have had a true beginning, but has existed forever in a succession of bounces. This vision broadens our understanding and nurtures the idea that cosmic history could be much more vast and surprising than we thought. Imagine a vast cosmic setting beyond what we can observe today. In this grand scene, one name often comes up: Roger Penrose, a renowned physicist and mathematician. He proposed a fascinating idea: conformal cyclic cosmology. At first glance, this concept defies our intuition, as it suggests that the history of the universe is not limited to a single beginning or a definitive end. On the contrary, each end of the universe gives way to a new beginning through a subtle transformation based on the principles of conformal geometry. Conformal geometry involves stretching or contracting distances precisely while preserving angles. In Penrose's vision, this property links the universe to both its final state and its initial state. When it becomes extremely cold, empty, and massless, it can be reshaped to resemble a hot, dense beginning. The key question then is to understand how mass disappears at the end of an eon, paving the way for a new cosmic cycle. In this theory, an eon designates the complete history of the universe, from the Big Bang to a distant and diluted future. When this future almost fades, it reaches a condition that, through conformal transformation, can be likened to a new Big Bang. Thus, the classic initial singularity is replaced by the idea that one eon succeeds another in an infinite loop. The loss of mass in the cosmic fluid makes this space-time reset possible. To explain the disappearance of mass, Penrose envisions that the Higgs field, responsible for the mass of many particles, collapses in a distant future. Over the course of expansion, particles that draw their mass from it would see it decrease, then disappear. This field, omnipresent in the universe, gives particles like electrons their massive character. If its intensity weakens, these particles would become almost massless, facilitating conformal reconfiguration. The notion of an eon is further illuminated when imagining that the infinite future and the infinite past are linked by a conformal transformation. At the very end, the universe becomes so sparse and thermally uniform that it reaches a geometry where all distances can be redrawn. In this scheme, the infinite future of the previous eon corresponds to the Big Bang of the next. This perspective suggests an infinite sequence of cycles, without a singularity in the traditional sense. Each new cycle inherits the global structure left by the previous one. To make this idea concrete, physicists are looking for clues. A key prediction is the existence of unusual circular patterns in the cosmic microwave background, the fossil radiation of the universe. According to Penrose, concentric circles of slight temperature variations could result from violent events of a previous eon, like the merging of supermassive black holes. These structures would be distinguished by a particular distribution of their intensity. The theory also predicts an abnormal distribution of gamma-ray bursts of high-energy radiation originating from cosmic events such as the collapse of massive stars or the collision of neutron stars. In this context, one would expect to detect a subtle anisotropy in their distribution, like a discrete imprint of past aeons. To verify these scenarios, Penrose's collaborators explored data from the Planck satellite. They found unusual circles in the temperature distribution, suggesting an ancient cosmic signature. Other researchers analyzed these results to see if the effect exceeded statistical fluctuations. A lively debate ensued. Are these real clues or artifacts related to the complex structure of the cosmic background? Similarly, the possible anisotropy in gamma-ray bursts divides the community. These phenomena are rare, and their localization depends on complex observations, with variable sensitivity across different regions of the sky. Determining a reliable anisotropy requires comprehensive data and strict control of instrumental biases. Attempts to detect alignments remain mixed, and caution is advised. These uncertainties do not render the theory unfounded, but show that it relies on delicate signals to extract. The vast volumes of modern cosmological data allow for multiple interpretations. Statistical techniques are progressing, but debates remain intense. Penrose and his supporters refine their arguments, convinced that solid evidence will eventually emerge. Others see rather random or instrumental effects. A major critique questions the physical feasibility of the gradual disappearance of mass. Must the Higgs field really decline? Could it remain stable? We still ignore many aspects of high-energy physics and the laws governing the ultimate expansion of the universe. The decline of the Higgs field remains speculative, and Penrose admits that key elements await confirmation. Other criticisms focus on the use of conformal transformations. They require precise adjustment of the space-time metric, and that all physics follow this reconfiguration. However, matter, radiation, and quantum effects do not always easily comply with this symmetry. The coherence of the cyclic scenario may require further adjustments. Despite everything, the conformal cyclic cosmology is appealing. It offers a unified vision, where each aeon transmits an imprint to the next. If it proved correct, the universe would experience successive breaths, escaping a cold, solitary end. It encourages the search for unusual signatures in the cosmic microwave background and questions the stability of mass in an extreme future. Methodological critiques on the circular imprints emphasize that detection heavily depends on the filtering method and the choice of statistical parameters. Specifically looking for circles increases the risk of finding them by chance in the massive data. The robustness of these signals remains to be demonstrated. In science, we always compare observations to a null model, excluding the sought effect. If the probability of obtaining the observed phenomenon by chance is too low, we conclude that it is real. In the case of the circles, many consider that the level of confidence remains insufficient. In the end, this theory illustrates the creativity of theoretical cosmology. Roger Penrose, with his work on black holes and space-time, has drawn attention to this singular idea. Even criticized, it stimulates the quest for observable phenomena capable of transforming our understanding of the universe. The statistical controversies show the rigor with which science examines each hypothesis. The conformal cyclic cosmology still has steps to take to convince. But the history of cosmology is full of ideas that took generations to establish or disappear. Research continues, and the exploration of the cosmic microwave background and gamma-ray bursts remains active. For Penrose, the beauty of this theory is to abolish the initial singularity as an absolute boundary. Time does not break. It reconfigures itself, driven by the gradual disappearance of mass and the resurgence of a conformal geometry. The universe would then be eternal, each distant future becoming a new past. The conformal cyclic cosmology illustrates our desire to understand the universe beyond established frameworks. The concentric circles of the cosmic microwave background and the anisotropy of gamma-ray bursts are promising, albeit sometimes contested, avenues. But it is in these debates that cosmology renews itself, enriching our perspectives on the origin and destiny of the cosmos. Validated or refuted, Penrose's proposal will have broadened our intellectual horizon, driven by the curiosity and questioning that drive science forward. At the heart of the cosmological scenario called the emergent universe, the central idea is that there is no true zero instant as conceived in the traditional view of the Big Bang. The history of the universe would not begin with a dense and fiery singularity, but with an initial stable or nearly motionless state. This quasi-Einstein static universe corresponds to a space-time curvature close to what Einstein imagined at the beginning of his work before adopting the concept of rapid expansion. In this model, the density of matter and energy as well as the geometry would remain almost constant initially until a mechanism triggers a progressive expansion, leading to a moderate inflation. This transition, regulated by an adjusted cosmological constant, would stretch space repeatedly without going through a singularity. We will explore step by step how a universe can emerge without a zero instant, evolve with stability, and be tested by observation. Let's start by defining what a static universe is. In general relativity, maintaining such a state is difficult. Gravity attracts matter and causes contraction, quickly creating instabilities. Einstein, wishing for an immutable universe, introduced the cosmological constant, a form of uniform energy exerting a repulsive pressure. If this energy perfectly balances gravity, the universe appears static. This configuration, called Einstein's universe, is nonetheless unstable. In the emergent model, an initial quasi-stationary configuration is proposed, whose curvature is close but not identical to that of Einstein's static universe, robust enough to avoid immediate collapse, gradually initiating an expansion. The objective is to avoid the initial singularity, a theoretical point of infinite density and temperature where general relativity and quantum physics clash. In the emergent universe, if the initial state is stable and relatively cold, there is no need for a violent beginning. The universe could have always existed in a static form without a true birth, with a potentially infinite age. The next question is, how does a stable universe begin to expand? Here comes gentle inflation. Unlike classical, ultra-rapid cosmic inflation, this slow expansion would be fueled by a cosmological constant, or a scalar field, acting without causing extreme exponential growth. Space would expand sufficiently to ensure spectacular long-term growth, but at a moderate pace. This gentle inflation has two major roles: to homogenize the universe on a large scale, explaining the uniform temperature of the cosmic microwave background, and to generate small density fluctuations at the origin of galaxies. In this view, the scalar field remains inactive at first, then gains importance, accelerating expansion gradually. The so-called Einstein-Lemaitre solutions revisit the general relativity equations with a cosmological constant, but with stable initial conditions. Energy density, pressure, and scalar field behavior are tuned to avoid collapse or explosive expansion. The cosmological constant must be large enough to trigger expansion, but not to the point of reproducing classical inflation. The question of stability remains. Can small perturbations destabilize this state? Some hypotheses show that it can withstand perturbations, notably rotational ones. Initial parameters must be adjusted for the stationary phase to maintain itself until the gentle inflation is triggered. The idea that an expanding universe could have an infinite age is surprising. If the quasi-static phase lasted eternally, there is no zero time. An internal event, perhaps a quantum fluctuation, would have initiated gentle inflation, leading to the evolution towards the current universe. To be coherent, this model must allow for the formation of light elements, explained by primordial nucleosynthesis. In the emerging universe, this hot phase could occur during or after slow-roll inflation, producing the same abundances as today. It must also explain the homogeneity of the cosmic microwave background. The infinite past of the quasi-static state would have allowed large-scale information exchange, ensuring a uniform base before the expansion. The model also predicts the absence of certain superhorizon fluctuations expected in other scenarios. Large wavelengths would have had time to adjust before inflation, reducing the presence of uncorrelated modes. This point could be tested by the detailed study of the cosmic microwave background. The infinite age also raises the question of entropy. Why hasn't the universe already settled into a heat death? Proponents of the model argue that the low initial density and temperature, along with a particular equilibrium, allow for a slow increase in entropy. This scenario could also better align with certain approaches linking general relativity and quantum mechanics, as it avoids the extreme conditions of a singularity. Future observations, particularly those on the distribution of structures and the signature of inflation in the cosmic microwave background, could help distinguish this model from classical inflation. The major advantage of the model is eliminating the question of an absolute beginning. However, it must explain how the initial equilibrium could last and why the cosmological constant has precisely this value. Testing an infinite age remains complex, as observations mainly pertain to the post-inflation universe, with the deep past being partly obscured. Finally, envisioning a universe without a beginning changes the perspective on cosmic time. As in certain cyclic or bouncing scenarios, there is neither an absolute beginning nor an end, but a history potentially extending infinitely. Welcome to the exploration of the refurbished Milne universe. Imagine traversing a vast cosmic horizon where nothing seems ordinary. Here, space exhibits a negative curvature, and matter is nearly absent, giving way to an almost total vacuum. This idea, initially formulated in a simple form by the mathematician and cosmologist Edward Arthur Milne in the mid-20th century, is being revisited today to align with recent observations on the evolution of galaxies and the luminosity of distant supernovae. In this conceptual universe, the dense and hot standard Big Bang model gives way to a surprisingly empty space. Nevertheless, researchers strive to integrate it into the current scientific framework. To understand the origin of this vision, one must delve back into the intellectual effervescence of the first half of the 20th century. Einstein's general relativity equations were still subject to intense debate, and new cosmological models were emerging. Milne then proposed an almost empty universe, with infinitesimal content and a hyperbolic geometry characterized by negative curvature. This type of space is distinguished by a shape that curves in two opposite directions, resembling a saddle. In technical language, negative curvature corresponds to a parameter, k, equal to -1 in the geometrical description of the universe. This defines an open space with an immensely large radius of curvature. Unlike closed or flat universes, Milne's implies an infinite space, devoid of any internal boundary. It can be imagined as a carpet endlessly unfolding without ever forming a loop. In this environment, the distance between galaxies evolves according to a law directly linked to proper time. Proper time here refers to the time measured by a clock accompanying the observer. The Milne universe, in its simplest form, adopts a geometry close to that of Minkowski spacetime, where light travels at a constant speed uninfluenced by matter or energy. By choosing a specific way to measure time, Milne demonstrated that this geometry could mimic an expanding universe, interpreting the redshift of galaxies as a purely kinematic phenomenon. Redshift, noted as Z, is a key element of cosmology. It is generally explained by the expansion of space, which stretches the wavelengths of light emitted by distant galaxies. In the Milne universe, this effect results from inertial movement rather than space expansion. This kinematic redshift offers a radically different interpretation of the observed phenomenon. This elegant approach reproduces some apparent effects of the expansion, but it confronts a pillar of the standard model: primordial nucleosynthesis. In the classic scenario, the initially dense and hot universe allows for the early formation of hydrogen and helium. In a nearly empty universe like Milne's, this phase does not exist, and the composition and light elements cannot be the same. How, then, to explain the presence of these elements? Proponents of the model have considered local processes or exotic scenarios, such as giant stars or extragalactic collisions. But these explanations remain cumbersome and less convincing than the simplicity of the standard model. To better match observations, some have proposed introducing a particular matter called X matter. This hypothetical matter would interact very little with the rest of the universe and would be uniformly distributed, making it undetectable in our daily lives. The evolution of the density of this X matter is crucial. Unlike ordinary matter whose density rapidly decreases with expansion, it should decrease more slowly to match observations of distant supernovae. It is hypothesized to vary proportionally to 1 plus z to 2, which allows for the adjustment of observed luminosity curves. Simply put, z increases with distance. The further a supernova is, the higher its z. Type Ia supernovae, serving as luminous references, show that this evolution of X matter makes it possible to reproduce the observed measurements in a Milne-like framework. However, this adaptation raises new questions, notably about the origin of the cosmic microwave background this fossil radiation at a temperature of 270.4 Celsius. In the Standard Model, it is the light released 380,000 years after the Big Bang, with an almost perfect blackbody spectrum. In the revamped Milne universe, another mechanism must be imagined to generate this uniform radiation without an initial dense and hot phase. But this complicates the explanation of the observed large-scale homogeneity. It is also necessary to account for the fluctuations of this radiation, interpreted in the Standard Model as acoustic oscillations of the primordial plasma. In an initially empty universe, their origin remains problematic, further weighing down the model. The formation of large-scale structures poses another challenge. In the classical model, dark matter and ordinary matter aggregate under the effect of gravity, forming galaxies and clusters. In the Milne model, different gravitational laws, or an unusual initial distribution of matter, must be conceived. The interest of the revamped model is that it interprets redshift as a velocity effect, not space expansion. This attracts attention when tensions appear in cosmological measurements, but to compete with the Big Bang, it must reproduce all key observations. It also remains to specify the transition between an empty universe and a universe where X matter and ordinary matter influence the global dynamics. Hypotheses vary. Some imagine abundant X matter in the past. Others see it as more discrete, with a universe inflated by a purely kinematic mechanism. To explain EA supernovae, the Milne model attributes their apparent low luminosity to velocities of recession, not space expansion. With X matter evolving as 1 approximates 2, it is possible to reproduce luminosity data while maintaining an almost Minkowski spacetime. But the acoustic spectrum of the cosmic background remains a major obstacle. Observations reveal frozen oscillations in the primordial plasma, difficult to justify in a nearly empty universe. The large-scale structure poses the same difficulty. Galactic surveys show a complex cosmic web, which, according to the Standard Model, results from the growth of small initial fluctuations. In a Milne universe, another process must be invented to achieve this network. Therefore, despite its originality, the renovated model remains less robust than the Standard Model, which explains the cosmic background radiation, nucleosynthesis, galaxy formation, and Type Ia supernovae in a unified manner. The Milne scenario requires multiple additions that stray from its initial simplicity. For some, this complexity is an asset. It offers a testing ground for our hypotheses. If one day it were demonstrated that the redshift is purely kinematic, it would revolutionize cosmology. For now, no definitive proof exists. Current measurements show an almost flat universe, whereas Milne assumes a negative curvature. This discrepancy makes the hypothesis difficult to support unless the model is further modified at the risk of straying from its original concept. Defenders of the model are working to adjust its parameters to align with modern data, a delicate exercise that can lead to inconsistencies with other observations. This model invites reflection on the nature of the redshift and the structure of spacetime while encountering major difficulties, explaining the abundances of light elements, the homogeneity of the cosmic background, and justifying the X matter. Even when marginal compared to the Big Bang, this approach remains of interest as an alternative avenue. Perhaps future observations or theoretical advancements will shine new light on it. At the heart of the most daring research in cosmology, the Janus Cosmological Model, or JCM, arouses both curiosity and enthusiasm. Designed by Jean-Pierre Petit and Gilles D'Agostini, it proposes an original alternative to explain certain phenomena of the universe without resorting to dark matter or the cosmological constant. We will explore the history and principles of this two-sheeted universe, where positive and negative masses reinterpret gravity and cosmic expansion. This innovative conceptual framework stands out for its bimetric vision of reality. If the idea of two metrics is surprising, following the author's reasoning step by step reveals a theoretical construct aimed at resolving puzzles such as the shape of galactic rotation curves or the recent acceleration of expansion. This journey will take us into the depths of an apparently familiar universe, but governed by a mechanism of mutual repulsion between worlds of opposite masses. To understand the JCM, one must return to Einstein's general relativity, where space-time is described by a metric that links distances and time. Janus takes up this principle but doubles it. Two spacetimes coexist, called G plus and G minus. Each obeys its own equations, and geometric properties differ according to the mass's sign. The challenge is to study how these two sheets interact and produce observable effects, such as galaxy stability or cluster formation, without invoking large amounts of dark matter. At the center of this theory, the constant epsilon plays the role of a link between the two metrics. While general relativity uses a single equation to relate curvature and energy content, Janus employs two, modified for each sheet. The epsilon constant determines the intensity of the interaction. Strong, the worlds couple closely. Weak, they coexist almost separately. This formalism, although theoretical, aims to explain phenomena such as galaxy rotation or the dynamics of cosmic expansion. In the Standard Model, dark matter is necessary to understand why galaxies do not break apart, despite their rotation speed. Janus proposes a different approach. The presence of negative masses modifies gravity on a large scale. This system, where positive and negative masses interact through repulsion or attraction depending on their sign, would explain galactic stability and the shape of rotation curves without dark matter. The JCM thus postulates two categories of matter: the positive mass of our visible universe and the negative mass of a mirror universe, difficult to detect. Theoretically possible, this negative mass interacts with the other only through the epsilon constant. This framework could reproduce the high speeds observed on the outskirts of spiral galaxies. Among the model's predictions, the flat shape of galactic rotation curves, due to the gravitational equilibrium between positive and negative masses, and a recently accelerated cosmic expansion without a cosmological constant, but stemming from the interactions between G plus and G minus. This combination allows dispensing with the two dark pillars of the Standard Model, dark matter and dark energy. The observation of type Ia supernovae, standard candles for measuring distances, is reinterpreted here. Their apparent luminosity would be influenced by the distribution of negative masses. This leads to a quasi-linear expansion, almost proportional to time, different from that predicted by the Standard Model. This scenario offers a perspective where the history of the universe depends on the evolution of two sheets, not a fixed cosmological constant. The rates of structure formation, such as galactic filaments, could serve to test this modified gravity. The JCM thus predicts distinct signatures in the expansion and growth of structures. Among the ways to verify the model, inverse gravitational lenses. While positive mass deflects light in a classical way, negative mass might deflect it differently, possibly even inverting the effect. Observing such a signature would be a major indication. The dynamics of galaxy clusters is another test. Their stability, attributed in the standard model to dark matter, could be explained here by a distribution of negative mass acting as a repulsive cavity. The cosmic microwave background, a relic of the Big Bang, might also bear the imprint of this bimetry, especially in its dipolar anisotropy. Precise measurements could reveal a pattern different from that of the standard model. While the idea of negative mass is not new, Janus makes it a central element, seeking to unify various observations: galactic rotation, formation of large structures, luminosity of supernovae. It is not a mere mathematical artifice, but a real and active component of the universe. Questions remain: quantum properties of negative mass particles, possibility of sign change, thermodynamic implications. These inquiries stimulate research and feed theoretical exploration. In light of the absence of dark matter detection, some scientists see Janus as a promising lead. The next steps: comparing its predictions with astronomical surveys, observing inverse gravitational lenses, analyzing cluster dynamics, and fine variations in the cosmic microwave background. By reinventing gravity with a repulsive dimension, Janus proposes a potential upheaval of our vision of the cosmos. But its validation will require precise and repeated observations. Whether it prevails or not, it illustrates the richness of paths that cosmology explores to uncover the mysteries of the universe. Since the beginning of the 20th century, Albert Einstein's general relativity has served as the theoretical framework for describing the expansion of the universe and gravitation. This model assumes there exists at the origin a singularity associated with the Big Bang, where physical laws cease to be valid. For many researchers, this singularity reveals a possible limit of the theory. In order to overcome it, some physicists and mathematicians have modified the Einstein-Hilbert action, which links gravity to the curvature of spacetime. The goal is to suppress or mitigate the singularity while explaining cosmic expansion without resorting to the traditional Big Bang. In general relativity, the action consists of a term related to the scalar curvature r, to which a cosmological constant and a matter density are added. In modified gravity models called f of r is replaced by a function f of r incorporating additional terms. One can thus add a term proportional to the curvature, squared, weighted by a coefficient alpha, or an inverse curvature term, multiplied by a coefficient beta. These adjustments allow for a better description of the extreme phases of the universe while maintaining coherent behavior in intermediate epochs. With these modifications, the function f of r can naturally generate an accelerated expansion phase without a dedicated scalar field. In the standard model, an inflation field is introduced to explain this rapid expansion just after the Big Bang. Here, the nonlinear terms of the curvature suffice to trigger a de Sitter-like phase, characterized by a negative pressure that accelerates the universe indefinitely. This approach offers a possible solution to problems like the cosmic horizon or spatial flatness. Contrary to the image of a violent Big Bang, where the universe immediately reaches extreme temperatures, some F-function of R models envision a gentler beginning. Sometimes it involves a gradual transition from an almost empty state to a dynamic phase. The equations then cap the maximum density and curvature, preventing any divergence. This stability can cause a bounce or slow expansion, leading to a regime where general relativity becomes valid again at lower energy. The universe thus appears without a true beginning or abrupt break. In this logic, the squared curvature terms associated with alpha favor a gradual acceleration, while the inverse curvature terms weighted by beta influence late expansion, potentially explaining dark energy without introducing a cosmological constant. Such a model can thus produce both a primordial accelerated expansion and a late expansion solely from geometric properties. To be credible, these models must pass several tests, including the speed of gravitational waves, the simultaneous observation of gravitational waves, and light from merging neutron stars requires this speed to be almost equal to the speed of light. The coefficients alpha and beta must therefore be adjusted to meet this constraint, or else be invalidated by multi-messenger observations. They can also affect the measured value of the Hubble constant, which describes the current rate of expansion of the universe and whose estimates vary depending on the methods used. Some F-function of R models modify the cosmic history to reduce this discrepancy. They can also affect the S8 parameter related to the growth of large-scale structures. If they manage to explain these discrepancies while describing the evolution of structures, they offer a serious alternative to the standard model. The formation of large structures depends directly on gravity. In the standard model, dark matter and general relativity explain the condensation of matter. In an F-function of R, gravity being modified, the rate of formation of galaxies and clusters changes. Some effects attributed to dark matter could stem from the geometry itself. Initial fluctuations then evolve differently, which needs to be verified by the study of the distribution of galaxies and clusters in the deep sky. However, difficulties remain. A too complex F-function of R can introduce additional degrees of freedom, manifesting as new fields testable in the solar system. To avoid their detection in dense regions, screening mechanisms like the chameleon effect are proposed. They mask these effects locally while allowing them to express at the cosmic scale. Despite these challenges, F-function of R models open the way to a scenario without a Big Bang, where expansion results from continuous geometric evolution. Eliminating the initial singularity remains a central goal, and some envisage combining these theories with quantum gravity to strengthen their coherence. The universe could then have always existed or gone through successive phases without infinite density. The de Sitter-type phase would naturally emerge without extreme initial conditions. Only increasingly precise observations and measurements will determine whether these theories will replace, complement, or refute the standard model. When we talk about metastable vacuum and cosmic decoherence, we enter a universe of vertiginous ideas where our cosmos could have originated from a shift between two energy states. In particle physics, the vacuum does not correspond to an absolute void, but to the lowest energy state for a field. Several configurations can exist, some more stable than others. A false vacuum is a locally stable state, but not optimal. Like a ball resting on a plateau before falling to the bottom of a bowl, this state can persist for a very long time before transitioning, due to a rare fluctuation, to the true vacuum at minimal energy. Such a transition could trigger a cosmological dynamic capable of influencing the entire evolution of the universe. To connect this notion to cosmic history, one thinks of the inflationary period, marked by a rapid expansion of space. The initially very high energy would have stretched the universe, making it almost homogeneous. If space was then in a metastable vacuum, this phase could have lasted briefly, accelerating the expansion and setting the conditions for our cosmos. The transition to the fundamental vacuum would then have released immense energy, heating the universe and multiplying particles. Cosmic decoherence explains how tiny quantum fluctuations gave rise to cosmic structures. It marks the transition from purely quantum behavior to classical behavior, where these fluctuations become observable on a large scale. In an unstable vacuum, bubbles can form, each transitioning to the true vacuum and becoming a local universe within a hypothetical multiverse. These bubbles could appear anywhere and any time, each evolving according to its own laws. This is the nucleation of bubbles in an eternal multiverse, a landscape of energy, states where inflation continues in certain areas, while, in places, a bubble emerges and expands. Within it, the energy settles at a lower level, and the universe that develops follows its own history. Our observable cosmos could be one of these bubbles. This scenario admits the existence of countless other bubbles, each with its own physical constants and trajectory. To test these ideas, one examines subtle details in the distribution of matter and radiation. The cosmic microwave background, a relic of the young universe, offers a privileged field. Uniform in appearance, it presents slight temperature fluctuations. A metastable vacuum could leave circular patterns or abnormal alignments. The strange correlation between the quadrupole and octopole is intriguing. Is it a coincidence, a bubble collision, or an unknown phenomenon? The question remains open. If our universe was born from a metastable vacuum, could it one day transition to a more stable state? This vacuum decay would be brutal. A more stable bubble would propagate at the speed of light, radically changing the physical laws and making life impossible. Although theoretically possible, this eventuality remains extremely improbable on our timescales, dispelling any immediate concern. The uncertainty regarding the ultimate stability of our vacuum feeds anthropic reflections. If a rapid transition were common, we wouldn't be there to observe it. Our existence suggests that this transition is rare or hindered by the parameters of our universe. Some see in this a fine balance of physical laws, conducive to life and cosmic longevity. Researchers are looking for clues, circular patterns in the fossil radiation, statistical anomalies, gravitational waves resulting from primordial collisions. So far, nothing conclusive, but leads persist. Increased precision on the mass of the Higgs boson and the top quark could reveal whether our vacuum is stable or not. Stability does not only depend on particles, it also plays out in the global dynamics of the universe, its expansion, its energy content. Numerical simulations explore bubble collisions or universes with additional dimensions, looking for characteristic geometric signatures. Cosmic decoherence visualizes as the freezing of quantum fluctuations on a cosmic scale, during the transition to a more stable vacuum. Each bubble would experience its own process, shaping galaxies and matter differently. This theory changes our perspective. Instead of a single universe, an infinite space-time where bubbles appear endlessly. Future observations of the cosmic microwave background, galaxy mapping, and detection of gravitational waves could confirm or rule out this tableau. The challenge is to distinguish statistical coincidences from real signatures, especially since only one universe is observable. Other models may explain some anomalies. Caution is therefore advised. The idea of future vacuum decay also raises philosophical questions. If it is possible, why hasn't it happened already? Perhaps there exists an infinity of universes where it occurred very early, preventing any life, and only the universes where it is delayed allow for our presence. Research remains active. Astronomical observations, particle physics experiments, advanced simulations. The next data could reveal asymmetries, unusual polarization of the cosmic microwave background, or concentric distribution of galaxies, possible signs of bubble collisions. Each aspect of these scenarios remains accessible to scientific verification. More precise surveys of the universe, gravitational and electromagnetic exploration, search for irrefutable traces in the cosmic microwave background. The confirmation of a future decay of the vacuum, even in the distant future, would radically change our vision of the cosmic future. Some believe these anomalies will disappear with better measurements. Others see in the metastable vacuum a promising avenue to understand quantum gravity and the ultimate structure of fields. Cosmic decoherence and the multiverse could be essential keys. Science advances by testing bold hypotheses. Anomalies in the cosmic microwave background, signatures of bubble collisions, atypical galactic structures, particle measurements. One day, an unexpected discovery could transform our understanding of the origin and destiny of the universe. Meanwhile, all speculations compatible with current observations remain open. The next surveys will guide our interpretation, whether or not they confirm the existence of a metastable vacuum. The question remains, what observations will force a paradigm shift? Bubble collisions, irrefutable large-scale anomalies, atypical gravitational wave spectra. Maybe we will discover a slight shift in the polarization of the microwave background, or a precise measurement showing that we live on an unstable equilibrium. For now, our universe remains remarkably hospitable. Maybe we are part of the rare bubbles, where stability lasts long enough for consciousness to emerge. And maybe, tomorrow, a tiny clue will overturn our vision of the beginning and end of everything around us. Research continues, searching for the observation that will open the door to a new theoretical horizon. Everything that begins has an end, they say. And if one follows this thread to the end, after tracing the path of cosmic origin, one naturally turns to the opposite horizon and wonders what will become of everything that exists. The universe has a history. It was denser, hotter, and simpler than it is today. It will also, tomorrow, be something other than what we know. To imagine its end, we do not need prophecies, but physics. The overall dynamics of the universe obey a few simple ideas: the expansion of space, the gravity that attracts, forms of energy that fill the cosmos, and the way these ingredients transform. On a large scale, the universe resembles an expanding fluid, described by a scale factor that dilates all distances with time. The key is the competition between matter that slows expansion and a mysterious vacuum energy that, on the contrary, drives it. Depending on which one prevails and how it evolves, the story ends differently. We will go step by step through the possible scenarios, keeping the language simple, but not sacrificing the essential ideas that allow us to distinguish them. Let's start by recalling why the universe is expanding. Observations of distant galaxies show that they are moving away from each other on average, and the farther they are, the faster this separation. It is not that the galaxies are swimming in a fixed space. It is space itself that is dilating. This expansion is quantified by a number that varies with the age of the universe, the expansion rate, and by a so-called critical density that separates universes destined to contract again from those that grow forever. Ordinary matter and dark matter slow the expansion because their gravity attracts. Light, as it dilates with space, loses energy, making it less and less important for the overall dynamics. And there is dark energy, a component with negative pressure that, if it remains dominant, not only makes the expansion persist, but accelerates it. How this dark energy behaves, constant or variable, moderate or extreme, decides the fate. If dark energy behaves like an immutable cosmological constant, expansion accelerates in a smooth but inexorable manner. In this case, the end resembles a long cooling, a slow extinction. It is sometimes referred to as a thermal death or big freeze. The image is simple to understand with thermodynamics. The second law states that entropy, a measure of disorder and energy dispersion, tends to increase. As long as there are differences in temperature or density, useful things can be done. Stars shine by burning their fuel. Planets dissipate energy. Chemistry creates complexity. But as the universe stretches, energy dilutes, temperatures drop, contrasts fade, and entropy approaches a maximum where nothing organized can spontaneously occur. It is an extinction due to a lack of gradients. Concretely, the chronology of a universe destined for the Big Freeze spans vertiginous timescales. Even today, stars are born in clouds of gas, but the gas reserves are dwindling. Massive, very luminous stars live fast and die within tens of millions of years. This process will end on the scale of billions of years, as gas is recycled less and less efficiently. Stars similar to our Sun, more modest, will live for billions of years. Some, even smaller, burn so slowly that they can shine for trillions of years. The universe will become mostly populated with discrete red dwarfs. Then, when even these have exhausted their hydrogen, with stellar remnants, white dwarfs cooling slowly, brown dwarfs never ignited, neutron stars, and silent black holes. Around some 100 billion years, no more new stars comparable to those of today will be born. Galaxies not gravitationally bound to ours will recede so quickly that their light will never reach us again, crossing a cosmological horizon beyond which information is lost forever. The Milky Way will eventually merge with its neighbor Andromeda and other galaxies of the local group, forming one large, isolated island, while other superclusters will disappear from the sky due to the accelerated expansion. During this slow agony, light itself unravels. Photons emitted today by the cosmic microwave background, already stretched in the microwave, will see their wavelengths extend to astronomical dimensions, rendering their energy negligible. Chemical reactions will become exceedingly rare as the average temperature drops. White dwarfs, these stellar cores the size of Earth, but as dense as a relaxed atomic nucleus, will slowly lose their heat and transform into invisible black dwarfs. If protons decay, it is not yet known, but if they do, their lifespan would exceed at least 10 to 34 years. Baryonic matter itself will volatilize over gigantic timescales, converting everything that remained into low-energy radiation and neutrinos. If, on the contrary, the proton is eternal, matter may persist indefinitely in the form of icy, dark objects, with the speculative possibility that black dwarfs reach exotic states and after unimaginably long times undergo slow nuclear fusion reactions triggered by quantum pressure. But such events, if possible, would be exceedingly rare and would not alter the general trend. Black holes, however, are not eternal if quantum mechanics is considered. They radiate very faintly, a process called Hawking radiation. The more massive a black hole, the colder this radiation and the longer it will take to evaporate its mass. A black hole with a mass comparable to that of the Sun would survive much longer than the current age of the universe, and a supermassive black hole at the center of a galaxy might exist for about 10 to 100 years before disappearing. These are almost unimaginable numbers. If we compressed the entire current cosmic chronology into a day, the final evaporation of the largest black holes would occur long after calendars cease to make sense. After this black hole era comes the dark era, where only isolated particles remain, extremely cold photons, perhaps some remnants of matter if the proton does not decay, and a cosmic temperature tending towards zero without ever exactly reaching it. No more structure, no more stars, no more chemistry, a thermodynamic silence. The frozen future is not the only possible end, however. Everything depends on the nature of dark energy. It is characterized by a simple parameter, the ratio of its pressure to its energy density. If this ratio is exactly -1, we are dealing with an immutable cosmological constant. If this ratio is slightly greater than -1, dark energy can slowly decrease over time, like a field that evolves. If, on the contrary, this ratio is less than -1, dark energy is called phantom, and its influence becomes stronger and stronger over time. In this latter case, cosmic repulsion goes wild. The expansion does not just accelerate, it diverges in a finite amount of time. This is the Big Rip scenario, the Great Tear. To imagine this, picture an elastic fabric stretching faster and faster. Initially, only the loosest seams come undone. Then the fibers themselves give way. In the end, even the molecules that make up these fibers are torn apart. If the universe is heading towards a big rip, there is a countdown. Long before the final moment, the largest structures, like clusters of galaxies, disintegrate. At a nearer time, the galaxies themselves can no longer hold together. The stars that compose them become orphaned. Even later, planetary systems are disrupted. Planets separate from their stars. Close to the end, the forces responsible for the cohesion of atoms and nuclei are overwhelmed by the unbridled expansion of space. Electrons are torn from their orbits. Protons and neutrons are separated, and even quarks can no longer remain confined. This progression follows a simple logic. As accelerated expansion becomes infinite, the characteristic size beyond which nothing can remain bound decreases, successively passing from the scale of clusters to that of galaxies, then stellar systems, planets, atoms, and finally particles. The final temporal wall arrives in a finite time measured from today, which can be on the order of tens of billions of years if dark energy behaves so extremely. The details depend on the exact value of the state parameter and its variability, but the mechanism is clear. The end comes not by slow cooling, but by universal tearing. One might wonder if this scenario is compatible with what we observe. Current measurements suggest acceleration, but nothing implies it is of the phantom type. If dark energy is closer to being a constant, the Big Rip can be avoided. However, it is important to understand that current cosmology is a snapshot of the present. Extrapolating into the future requires an assumption about the stability of dark energy. In any case, the idea of the Big Rip illustrates how precisely the form of vacuum pressure, a concept that seems abstract, can determine the fate of everything that exists, down to the atomic level. There exists a third cosmic narrative, older in human imagination, but today less favored by observations, that of a universe that stops, reverses, and collapses. This is the Big Crunch. Its logic mirrors that of the Big Bang. If the total density of energy, including all its components, exceeds the critical density and nothing accelerates the long-term expansion, gravity eventually wins. After an expansion phase that slows down, the universe reaches a maximum size, then contracts. At first, the contraction is gentle. Large structures come closer together, galaxies merge more often, and the average temperature rises because the gas compresses. Later, everything becomes an incandescent plasma. Atoms are dissociated, and light is trapped in a dense soup. Continuing the evolution, one arrives at a state of extreme density and temperature, a singularity of end time. One can then imagine a rebound, that instead of an absolute end, the universe shifts into a new expansion, like an elastic ball. This idea, called Big Bounce, leads to cyclic cosmologies where each world would be born from the thermal ashes of the old. The physics of a rebound is difficult because it requires going beyond classical general relativity and invoking quantum gravity effects at extreme densities. But conceptually, nothing prevents the contraction from resulting in a state where the equations change behavior and trigger a new phase of expansion. Why is this scenario considered unlikely today? Because the current expansion is not only unrestrained, it is accelerating. For the Big Crunch to occur despite this, dark energy would need to fade or reverse in the future, allowing gravity to regain control. Some theories allow for this. A dynamic field could see its pressure change sign. An exotic component with negative density could emerge. But as long as current measurements continue to indicate acceleration compatible with a cosmological constant, the Big Crunch will remain a theoretical possibility, more than a probable destiny. Beyond these three major families, cooling, tearing, collapsing, there are more exotic endings, which arise not just from a simple extrapolation of current ingredients, but from a profound change in the laws themselves. The universe, in modern physics, is not only made of particles and forces, it is woven by quantum fields that can exist in different energy states. Our vacuum, what we call nothing on our scale, could be just a false vacuum, a metastable state that is not the lowest possible energy state. In such a situation, the vacuum could drop to a lower state through a nucleation event, creating a bubble of a new vacuum that would expand at a speed close to that of light. Inside this bubble, the constants of nature, the mass of particles, and even the structure of forces could be different. The boundary between the old and the new vacuum would be destructive to the existing structure. If such a bubble reached us, it would instantly redefine local physics. The end, then, does not resemble either a tear or a freeze, but a cosmic phase transition, analogous to water freezing or boiling, but applied to the fabric of the vacuum. This idea has roots in field theory and hints from Higgs physics. However, it remains speculative on a cosmic level, as we have no direct observation of such a transition. Nevertheless, it illustrates a possibility. The end could come from a change of state, not just continuous evolution. Another general framework for thinking about the end is that of the multiverse and eternal inflation. In this picture, space-time is an ocean of perpetual accelerated expansion, where bubbles occasionally detach from the inflationary background. Each bubble is a universe with its effective laws, constants, and its own thermodynamic history. Ours, then, is just a bubble among others. If this picture is correct, our local end, big freeze, big rip, or otherwise, does not exhaust reality. It is a local condition in a much larger ensemble. The practical question becomes, can our bubble come into contact with another? A collision between bubbles would leave scars in the cosmic microwave background in the form of subtle geometric patterns. Such traces have been looked for. Even if nothing obvious has been found, the framework remains a conceptual laboratory where the end is no longer an absolute, but an episode in a cosmic froth. One can also imagine transformations of matter and energy that, without fundamentally changing the laws, lead to a final state very different from what the three classic scenarios suggest. For example, in a universe dominated by a cosmological constant-type dark energy, the distant future resembles a de Sitter space, characterized by a horizon beyond which we can never receive information. This horizon is not cold. It has an extremely low temperature associated with quantum radiation. Very far in the future, the physics of the universe may resemble that of an almost empty thermal bath, but not completely, where rare but inevitable quantum fluctuations appear and disappear. Most of these are of no interest. Some, extremely improbably, could produce complex configurations. This kind of consideration leads to philosophical paradoxes, e.g., fluctuation observers, but the physical message is simple. Even an accelerated vacuum is not absolutely immobile. It has a temperature, thus entropy, and it lives in its own way. To make these stories more concrete, let's return to the timescales and key stages. In a future resembling the Big Freeze, milestones succeed like a cosmic clock. In a few billion years, star formation significantly declines. Galaxies not bound to ours slip behind the horizon and become unobservable. After about 100 billion years, most solar-type stars have completed their life cycle, leaving behind stellar remnants. On scales of trillions of years, the last red dwarfs extinguish as they slowly but surely burn their hydrogen. In the degenerate era that follows, almost all stellar matter is found in white dwarfs and brown dwarfs, which cool. If proton decay exists, baryonic matter eventually breaks down into lighter particles over timescales at least exceeding 10^34 years. If it does not, black dwarfs may persist indefinitely. Much later still, from 1040 to 10^100 years, black holes dominate the energetic landscape, then evaporate, the smaller ones first, the larger ones later. By approximately 10^100 years, even supermassive black holes have vanished, leaving only isolated particles in an icy sea. In a big rip-like future, we do not count zeros, but follow a timeline relative to the final moment. Tens of billions of years before the tear, the universe still resembles ours, except the acceleration is more pronounced. A few billion years before the end, galaxy clusters fall apart. Millions of years before, galaxies burst. Thousands of years before, star systems disintegrate. Months before the end, planets are torn away. In the final moments, atoms themselves give way, then nuclei. At the final moment, the scale of the universe explodes towards infinity in finite time. Dark energy takes everything, and the very notion of structure ceases to have meaning. The temporality of this scenario gives it a dramatic aspect. It is not extinction due to lack of energy, but due to excess expansion. In a big crunch-like future, we can draw an inverse chronology of the Big Bang. First, expansion slows and then stops. Next, contraction begins. The average temperature increases. Radiations become more energetic. Light is compressed instead of being stretched. Galaxies continuously merge. Chemistry ceases due to the heat. Everything becomes a plasma. At a still later time, densities reach levels where classical descriptions collapse and quantum gravity must intervene. If a bounce occurs, it determines the initial conditions for a new expansion. If not, time crushes into a singularity. The distinction is conceptually clear but physically blurred, as we do not yet have the complete quantum gravity theory to say if and how a bounce occurs. Throughout all these stories, a transversal principle returns: thermodynamics. The universe is a machine for making entropy. Stars shine by turning temperature and pressure gradients into light. Galaxies form when gas loses energy and collapses under gravity. Life itself exists only because the universe has not yet reached equilibrium. In a future of thermal death, entropy tends toward a maximum, and the ability to do work dies out. In a big rip, entropy also increases, but because accessible states skyrocket as everything dilutes. In a big crunch, entropy increases again as contraction concentrates energy and creates very excited states. If a bounce occurs, it must dissipate accumulated entropy, or the next universe begins in a state very different from ours. This thermodynamic thread ties the ends to the arrow of time. The reason we distinguish before and after is rooted in the growth of entropy, and this growth does not, on a cosmic scale, intend to slow down. Scenarios can also be illuminated by the notion of horizons. Even in an infinite universe, what we can, in principle, see and influence is limited. In a future dominated by a constant-like dark energy, there exists a cosmological event horizon. Beyond a certain distance, light emitted now will never reach us, because the space between us and the source is stretching too quickly. This horizon creates a physical boundary for information. It plays a role analogous to the horizon of a black hole, with an associated temperature, however low it may be. As the future unfolds, our island of the universe shrinks in terms of what we can contact, even if the total space grows. In a big rip, this horizon approaches to the point of cutting ever smaller links. In a big crunch, the horizon becomes closer because light can travel a greater fraction of the universe, but this does not improve the fate of structures, as the increasing heat destroys the conditions of complexity. One question inevitably arises: what do the measurements say? Everything that can be measured today points to an acceleratingly expanding universe, dominated by a component with a negative pressure close to a constant. This favors a future that resembles a big freeze, softened by the quantum subtleties of a de Sitter space. But favored does not mean guaranteed. The state parameter of dark energy could be slightly different from -1. It could evolve slowly. A future transition is not ruled out. Modern cosmology is a science of the present. We reconstruct the past and extrapolate the future by projecting the laws tested today. The more precise our measurements are, the more solid our projections will be, but no finite precision will transform an extrapolation into absolute certainty. In this spirit, one understands why cosmologists like to present several endings. They are not equivalent fictions. Some are more compatible than others with the state of knowledge. They are rather compasses, each pointing to a different way of inhabiting the same set equation. The Big Freeze tells of the slow dissipation of differences until equality everywhere. The Big Rip tells of the runaway expansion until the fragmentation of every bond. The Big Crunch tells of the return to the primordial fire with the possibility of a new beginning. Exotic scenarios tell of a change in the rules themselves through a vacuum transition or a neighborhood between bubbles of a vaster multiverse. All in their own way take seriously the fact that the universe is not static, that the arrow of time is not just a psychological effect, and that local laws determine global destinies. There is, finally, a human dimension to this panorama. Thinking about the end of the universe is not meant to predict the fate of our lives. None of these scenarios plays out on the scale of a civilization or even a species. It serves to understand the place of organization and complexity in a world governed by simple laws. Why are there shining stars, temperate planets, and beings capable of asking questions? Because the universe has not yet reached equilibrium. The possible ends remind us that complexity is a transient phenomenon, born of gradients that eventually exhaust or are torn away. Whether the universe freezes, tears apart, collapses, or changes state, the cosmic story has a physical moral. Lasting order is not the final result, but a stage. This is precisely what makes this stage precious, and what makes scientific curiosity so fruitful, to understand, while there is still time, how it all works.